I think let's get started. So today what I have done is that I thought that uh, let's try to save some time because we have a limited time. So I've tried to create a template today, and we'll try to follow this template for our session. So today we are going to start with a queue data structure. Okay. For a queue data structure, basically it's first in, first out. So whoever who comes, the entry which is added the first time into the data structure will be the one which will be removed first. So this is the beauty of a queue data structure. So I've just given a very bad diagram down. For example, you might have, if you go for booking of a movie ticket, or if you go for a ticket reservation in the railway, right? The person who comes first and collect the ticket is the one who gets the first chance, right? So this is the first come first serve thing. So this is what the queue data structure is. So whichever entry that comes first is the one which will be uh, will be brought into the action. Okay, can you guys think of any use case where the queue data structure might be used? First come first something in your day-to-day computers use cases. I think most of you, I think Zahir, you are still in the college, but I think Paratosh, you are already working, right? So can you tell me a few of the examples practically where queue is being used?
Like for example, in games, say for example, if suppose the person is firing in the bullets or something, so we might create a structure of queue.
Okay, okay, makes sense, makes sense. Anywhere else that you see in the application that you have created? Uh, so, for example, if you have created a web application, suppose, okay, so suppose you have a web application like this, web app, okay, and suppose this web app that you have created is having say a QPS of say 100. What is 100 query per second? QPS is driven by how much the thread pool, right? So normally how many threads are there in your pool, that drives how much QPS your particular server can support, right? Now suppose what happens, there are clients calling your server, okay, and suppose the number of calls that this client is making to your server is say like 200 now, 200 concurrent calls. Okay. So what happens is that now your system is only able to support 100 calls at a time, 100 queries per second. But say number of concurrent call that is happening right now is 200, right? So you need to support this, right? You cannot say the remaining 100 people that go back, I'll not be able to give you the response, right? Because that would be a very bad customer experience. So normally what you do in that case again is that before call of the server, you maintain a queue kind of data structure here. Okay.
Okay.
And the 100 calls you are able to process, and the remaining 100 to queue it here.
Okay.
And then as and when your threads get free, you will pick this one, then you'll pick this one, then you'll pick this one, then you'll pick this one. So that is another way, one of the very common and the great use cases of the queue. So whenever you have to scale systems and which there's upper bound to your number of queries that you can do based on the pool size that you have created for your system. But still, if suppose in certain spike situations, the number of requests is more than that, you still maintain a queue where you don't lose your customer. Now, the response time will definitely be hit because they will be serviced later on, but still they will be given some service, right? Will they not be outrightly rejected? Okay, so that is one of the biggest use cases of the queue. Another use case of a queue is that you might would have heard about the messaging systems, right? Messaging systems
Yeah.
like Kafka.
Are you aware of the Signal R? Are you aware of that? I mean,
Signal R is an open source or it's a proprietary?
it's a real time messaging thing. Like for example, it is used in chat. Like basically
Okay,
we in C Sharp or in .NET profile we use that. And
okay,
for Java and open source, I don't remember, but definitely we use Signal
okay,
R for this. It
okay,
uses the same concept actually for the messaging.
okay, okay. Okay. So basically, yeah, the concept of the messaging system is simply publisher subscriber design pattern,
Yeah,
and
yeah,
there's multiple implementation of it. Most famous among are the Kafka, ActiveMQ, RabbitMQ, and even Redis to some extent, and maybe there's so many implementation. Even all the cloud providers have their own messaging system. For example, AWS has their own support for a messaging system. But whatever messaging system is, they all are powered internally because of the queue, because it's the queue which follows the first in first out order. So whatever the messages that were pushed in first is the one which will be taken out, right? So this is the beauty of what queue is. So understanding queue help us to understand these so many systems. Cool.
Okay.
Now coming back to the key terms in the queue, just like in our stack, we have a queue two key terms, which was a push and a pop. Similarly, in the case of the queue, we have a two terms. One is known as the N queue, and we have something called D queue. So N queue means is another term for adding element, add element, and the D queue is another term for removing the element. Okay, so whenever I have to add anything in a queue, I say that I'm enqueuing it, and if I have to say I have to remove anything, I'll be saying that I'm dequeuing it, right? And just like the stack in which the push and the pop has to be done in a constant time, similarly the queue also, the both enqueue operation and the dequeue operation has to be done in a constant time. So given a queue, you can take it for granted, right? You can take it for granted that its in-queue operation will be also done in the constant time, and its dequeue operation will be also done in a constant time. You don't have to worry about the underlying implementation. But if somebody tells you that okay, you are using a queue, it means that the in-queue operation should happen in a constant time, and the dequeue operations will also happen in a constant time. So the time complexity should be O of one of this one also, and O of one of this also. Okay. And that is how in any of a messaging system, right, here also, right, we are using queue data structure, because whenever we have to add any data or whenever you have to remove any data, it guarantees a constant time. So I get a very good performance advantage also, irrespective of the size of the queue, irrespective of the number of messages in this queue, or the number of messages in the Kafka, or your serial array or active queue. So whenever I have to push a data, or whenever I have to enqueue a data, or whenever I have to dequeue a data, uh, the time that it will take will always be constant, right? So that is the beauty of enqueue and dequeue is. Apart from that, few more things that we need to support in a queue data structure, which is like one is empty, which will say whether the queue is empty or not. The second one is full, and enqueue and dequeue we have already seen. Okay. So this is what on a high level a queue data structure is, and now we have understood where it is being all used, what kind of data structure it is, and what is the two key basic characteristic of a queue data structure. It is about enqueuing and dequeuing in a first in first out order in a constant time. So let's try to have a first implementation of a queue. Okay, and as we saw in the case of the stack, we were using array as an underlying implementation, our data storage layer. For the queue also, we'll first try to use an array to implement a queue. Okay. So for example, say first of all, if I say that 5 has been added, so it means I have to go and add 5 to it. So where should I go and place in this array? In which position the index 5? Should I go and put it in the 0th index? Should I go and put it 4th? Should I put it in middle of it? How should I go about it? Should we put it at the 0th position?
Yeah.
Yeah.
Okay, perfect. Let's try to put it at the 0th position. So I'll put 5 here. Okay. Now again, I'm trying to do q.enqueue7. Where should I put this 7 now? Index 1. Very nice. Then again, I have to put 9. So with your logic, I should go and put 9 here. Okay. Now I have to do a dequeue. Now if I have to do a dequeue, which element should it return? What should be the value that should get returned from this one? What should it return? If it is a first in first out data structure, what it should return? It should return 9, but 9 was the last one which was getting added,
five
right?
should return. 5.
The 5 should get it, right? Jahir, why are you saying 9? Again, I'm repeating, don't get confused, okay? Queue is a data structure in which whichever element which was added first will be, will be removed first only, right? So 5 was the element which got added first, then 7 was added, and then 9 was added. So when I say that I have to dequeue, the first element which was added will be removed from it, right? So when I say queue.dequeue, it should return me 5, right? So if it is the case here, then what will happen is that 7 and 9 and 0 space 0 position element will become empty, right? Everybody good? Agree on this?
Okay. So
Perfect. Again, when I do dq.dq, now you tell me what will come out as a part of q.dq thing.
7 should come out.
Seven should come out. So again, the seven also has come out, and now I'm only left with nine. Okay. Now when I do q.nq, where should the three go? Tell me, where should we place three now?
We should go
Uh,
on zeroth index.
the three should go on the zeroth index. Okay, if I go with Vivek, three should go at the zeroth index, and I put it here and put nine here. And if I suppose again, if I have to do q.dq, what should you do? Normally, I go and start picking from the left itself. So in this case, you will what will you take out? Will you take out three or will you take out nine? And try to think programmatically, because now as a human being we have a supercomputer mind, right? So I know that I have to take out nine, but if you're writing a program, you have to follow a particular pattern, right? You cannot keep on flipping between that. So far here, when you have to do, you first of all took out the element from here. In the second dq you took out the element from the here, so that is why you got 5 and 9. So basically you have it
Okay. Do we
dequeuing it from the left. Yeah.
Hello? When we are dequeuing an element, should we actually change the position of other elements also?
Now, if we start changing the position of the other elements as a part of DQ, that time complexity will be compromised, right? The time
Okay.
complexity, as you remember, I said the beauty of the queue is that the time complexity should be constant, whether it's an NQ operation or whether it's a DQ operation. But doing the NQ and the DQ, if you start shuffling the positions, that will take linear time, right? The time complexity will start suffering.
So in this case, 3 should be added to third position, I guess, because
Yes. So ideally, yes, you are right. So the three should be, should not be positioned here. Whenever I say the three should get positioned to the next position of nine, because this is what we are trying to do the programmatically, right? So the programmatically we are saying that whenever I have to add any element, right? Whenever I have to add any element, I'll add to the right of it, and whenever I have to delete any element, I'll do left to it. So for example, in this case, uh, at any position of time, this is the pointer uh, towards which we have to enqueue it, right? We have to enqueue it, and this is the pointers where we have to dequeue it. So uh, in the stack, if you remember, from the same side where we were adding element, from that side only we were also removing the element, because that time we wanted to have the first in last out or last in first out order. But in this case, since I have to have the first in first out order, so in one direction, if I'm adding the element, from another direction I'll be picking out the element. So always the element will be added to the right of it, and always the elements will be dequeued or removed from the left of it, right? So again, if I do one more thing, q dot nq and say 9, so again, what we'll do is that if I just create this one, so it will be 9, it will be 3, and again 9 got added. And again after that, if I want to do 10 to this, uh, what I see, I don't have any space left, so I won't be able to add any element to it. So even though the array has 3 elements left, right, still I will not be able to add any element to this particular array. So if we just try to implement queue with this array way of implementing it, what is the problem that we are facing? What is the issue with this approach? Can you guys tell me what is the issue with this?
Wastage of space.
Wastage of space. Very nice. So if we try to implement queue using a one dimensional array, we can definitely attain both the nq and the dq in a constant time. That is not a problem. But the biggest problem is the wastage of space. Even though the array still has few spaces left, still you will not be able to use it, because every time when you are trying to dequeuing it and every time you are trying to enqueue it, your positions keeps shifting, and once you have moved from one position to the right, you cannot use that space, right? So whatever this space that we have been left with, right, this whole space, this whole space, right, this is a wasted space, wasted, right? This is wasted. So this is one of the challenge when we are using array implementation. Another challenge is that array is always a constant size data structure, right? So that challenge already existed before also. So since array is a constant size data structure, if I want to have a dynamic size queue, again that is a challenge, because I cannot have more than 5 elements in a given array, because if I have a defined array of size 5, right? So that is another challenge. I asked you, I made you guys think about in this direction because I want a solution. So if this is a problem, can we do anything in this array to solve this problem? Can you guys think of any solution for this particular problem?
Should we dynamically increase and decrease array size?
Array size dynamically we can definitely increase and decrease. That will help us definitely in one of the problem, which is fixing the constant size of the array. But this wastage of space will still be there, right? So what we can do in this case is that one possible solution of that is circular array implementation. Uh, basically, to tell you, there's nothing as such called circular array. Okay, there's nothing as such called a circular array which exists. But basically, what we try to do is that we try to represent a one-dimensional array into a circular array. What it means is that suppose I have a one-dimensional array like this. Okay, and suppose I started moving in this direction from the left to right. Suppose started moving in this direction from the left to right. And as soon as I enter the last element, after that there is no position left. So if suppose I'm here, then I move here, then I move in this block. So it was starting at 0, 1, 2, 3, 4, and 5. And as soon as I have to move after 5, I'll again come back to I'll again come back to 0 itself. So some way if you can enable this movement from the last to the first one, this array can start behaving like a circular array, and then we can treat it as if it is a circular array. So let's first try to see if suppose the circular array exists, can this problem of the wasting of the space can be fixed? And if it is fixed, then we will be using the single array itself, but we'll try to write a code to manage this overflow. Like whenever I am at the index 5, again after that it should not go to the index 6 because it will give the array out of bound exception. Rather, I should jump to the array index 0. Make sense?
Yes, sir.
Perfect. So let's try to see the same thing and see how it works. So suppose uh, this is my starting point, okay? And in the starting point, let's me tell me, uh, say like you have two things. You have a front pointer and you have a rear pointer. Okay. Front pointer is where you keep on adding elements. Okay, adding elements. And suppose rear is the point from you remove the elements. Okay. So adding means NQ and removing means DQ. Right. So first of all, the one was added. Okay. So one was added. So one comes here. So one here is also my front also, and one is also my rear also. Now when I include two, uh, I put two here, and now my F is this index, but my R is still this one only. Okay, makes sense. And again, if I do q dot nq3, the q3 will come here. No, and now F will be this one, and this will get deleted. Right. Similarly, when I do 4, now my finally F is here. So this is so far this is the the situation is like this, in which my rear is still at that position and the front is this one, right? So now suppose till this point it was all fine, right? Till this point it was all fine. Now I'm trying to dequeue it. Now from where I should remove the element, guys? Which one should get dequeued? What should return? Q dot dequeue should be what?
1.
Very nice. So once I get the value as 1, uh, this space gets vacant, right? So what we'll do is that we'll delete this. Right? We will delete this, right? And my rear position will now no more be this. Now I'll be my rear position will become equal to this, right? And then suppose I'm again dequeuing it this here. So again when I'm dequeuing, now the rear is 2, so it will return 2. this will also get deleted, this element, and my rear will move from here to my rear will move to this position, and then again when I do a NQ, now this will be 5, and now this will be a new front, right, and this will get deleted. So what I see is that if I use this kind of data structure, I will keep on enqueuing. So now if I have to suppose enqueue q dot enqueue 6, then 6 will get added here. Then if I again do q dot enqueue 7, 7 will get added here. Q dot enqueue 8, then 8 will get added here. Then if I do q dot enqueue 9, then 9 will get added here. Q dot enqueue 10, then 10 will get added here. Right, this is 11. So what happens in this case, what we see is that the since it is circular in nature, it is circular in nature, so we are not wasting any space. So the problem which was there in the earlier implementation of the array, because of the enqueue and the dequeue thing, we were wasting lots of space. In this implementation, we are not losing any space. Is it making sense, guys?
Yeah.
Now we'll try to do a implementation of this. We'll try to do a implementation of this. Okay, and we may say that from the point where we started, that maybe a point will be, let's call that index to be, this was index 1, index 2, 2, 3, 4, 5, 6, 7, 8. Suppose this is like this one. Now let's try to see a code how to we implement this circular array. I'll try to write it in Java, but you guys can feel free to change into your language of choice. As we decided, our common language will be Java. So in Java, everything is a class. So we define public, and suppose the class is Q. Okay. And as we already said, the Q should support the following methods. So one is enqueue, dequeue is full, and is empty. And everything is in a constant time, O of 1, O of 1, O of 1, and O of 1. Okay. Now let's try to implement each method one after the another. Let's try to implement first, and the underlying data structure that I'm using is int array. Okay. And let's try to also have a capacity. Right. So define public q in capacity. What we do is that this dot capacity equals to capacity, right? And we define array equals to new int, and I pass here capacity. Right. Okay. Now the first thing that I have to write is public boolean is public boolean is empty. Okay. So my data structure is like this. Now, can you tell me what should I say? Now, let me add also one more thing. Like what is my, so two more things like int front and int real points. So initially it is starting, so I can say that front is equals to this one, maybe real is also. So for the is empty condition, what should we write inside this is empty condition, guys? What is the code should go like for the is empty one?
If front is equal to rear.
If front is equals to rear, that will also can happen when there is one element, right? That is not implicit, because if there is only one element, when suppose I have just added first element, say say I have added element say 9, right? So in that case, front is also this, and this is also rear, right? So front is equal to rear, right?
Front,
So this is not empty. See, when there is only one element, even in the case of the linked list, we saw head is equal to tail
yes.
when number of element is one.
Yeah, yes.
Same in the stack. So if there is only one element, then there is what rear and there is what front. Doesn't make sense, right? Both are the same thing. So if the front is equal to rear, it doesn't guarantee that this is empty.
Like front should is rear minus one. If
Front should be
like
rear minus
one.
1. So if front and the rear are at the two different position, right? Then it is definitely that it is not empty, no?
No, I will start for like front from minus one initially. Front from minus one and rear should be at 0. Like
But why the rear should be at 0? So if the rear is at 0, it means that at 0 you also have some element. And if suppose if there is no element as such, and you are saying that rear is equal to 0, what you will try to do? You will try to dequeue the element from 0 position, which actually is not existing. And in the starting of initialization itself, I have defined this condition: right? Front is equal to 1 and rear is equal to minus 1. Right. This is my starting position because I know that if I have to dequeue, enqueue any element, I will go at the front position, and if I have to dequeue anything, I'll go to the rear position. Initially, both the front is minus 1 and the rear is minus 1. So suppose I have to add a new element, so I'll go to the next front. Minus 1 plus 1 equal to 0. So at the 0th position, I'll go and do it. But right now, when the rear is equal to minus 1, if I have to dequeue it, I cannot dequeue it because there is no element in it. So this is what my situation is. Front is equal to minus 1 and rear equals to minus 1. So it's very simple. If it is empty, how do we figure it out? We just say that if front is equals to minus 1 or rear is equals to minus 1, return true.
No, but my question to you is like, suppose if you added 5 elements and front and rear reaches to a fifth element, if that is the fifth element, okay. So from 1 to 5, if
Uh-huh.
you're adding that and you're dequeuing it, so you mean to say automatically both the front and rear indexes they get target to minus 1
Yes,
internally.
we'll come to that. I got you one very genuine point, and we'll come to that. So we'll have to take care of this thing when I'm trying to do a DQ. I'll have to take care of this one. That when the array gets empty, all the elements are there's no such element in this. We should reset both the front and the rear to the minus 1 index. We'll come to that, and that way it will make sense because someday we'll have to define this. Otherwise, it will become very complicated, right? So we'll see that when we are trying to dequeue and we are reaching a state in which there is no more element left in the given array. In that case, we'll put both the front equals to minus 1 and rear equals to minus 1 again. So that always this empty check can be valid. So we only have to check whether if the front is equal to minus 1 or array, or rear is equals to minus 1, it means that it is empty, otherwise we'll return false. Okay.
Okay, fine.
Okay. And then second one is that public boolean is full. Okay. Can you tell me how do we define when it will be full? So suppose I keep on adding element into it, right? So for example, uh, 9, then 7, uh, 9, then 7, maybe 15, then 4, then 8, 2, 1. Now once I have come here, I say that this is empty. But how do I say it? Right now my front is this one. This is my front, and my rear is this one. Rear is this one. Okay. So if I say that front plus 1 is equal to rear, can I say that this is the state when I'll say that this is full? Can I say that?
Yes, you can do that.
Okay. So what I can say that return f plus 1 equals to r, right? But I see there is a challenge in this statement. What is that? Can you guys figure it out?
I think the index values. I mean, in this case, f plus 1, like uh, front is at index number 6. 6 plus 1, 7 is equal to 0. So
Yes. So what should we change here? Very nice. Very good. Very good. Jahid. So what should we do to fix this up?
I can do another condition like when my friend is at last index, the rear should be at zero index, something like that. I don't.
That is very hacky code. We should
Okay.
always try to avoid hacky code, right? This is
Okay.
a kind of hack, and this will unnecessarily add too much of bugging. What you can do is that you can make use of something known as ampersand. If you remember in the array thing also, I told you a logic in which using the ampersand and the division operator, you can store two kind of information in the same array. That was very strong thing. And I asked you guys to please note it down somewhere because that is
Yes,
something
right.
which is very helpful. That is very helpful, right? So
Mm.
here also we can make use of that. So what I can do is that I can just write instead of f plus 1, I'll just write f plus 1 percentage capacity.
Mm.
So what it will do is, so here, what where it is 6, so it will do 6 plus 1, and then when I do percentage 7, value will become equals to
Zero.
right. But if the value was less than that, suppose I am right now at 5 only. So if I do 5 plus 1 and then I do 7, it will still remain 5 only. So it will only come into the action when we are about to exceed the array bound, upper bound. It will give us, it will correct us back. So basically this is the thing, this ampersand thing, this is that magical weapon which is actually trying to, so actually there's nothing called a circular array. Okay, so we are actually still dealing with a linear array only, right? Linear array only, like this only, so it has element like this only. But as soon as you are reaching here, because of this operator, you are again being guided to this position, and it behaves as if you are working in a circular array. Is it making sense?
Yeah.
So there's nothing as such called a circular array. I'm again repeating. At the end of the class, you shouldn't get confused. There's something called circular array. There's nothing called circular array. There's only was this linear array that we have. But in the linear array, with the help of this operation, which is the ampersand or the modulus operator, right? We are trying to uh, make it behave like a circular array, right? This is very important. This is being used here in the array also. We have used it, and the several places throughout the data structures and algorithm, we will be using this concept, to avoid any kind of overflow from an array. Overflow from an array. Cool. Now let's move on. So now we are done with the isEmpty implementation. We are done with the isFull implementation. The next implementation is about, let me draw this again here. Something like this, okay? And right now this is my, this position is my rear, and suppose this is my front position, okay? Given this situation, I have to now write code for two things. So first one is that public void enq, okay, and int data. What is the first thing that should be right in this enq implementation, guys? What is the first thing that we should check?
If it's full or not. If it's full
Yeah,
or not.
very nice, very nice. If is full, uh, then you simply return, don't do anything. Or you can, if you want, you can throw some exception also, that is, uh, q q is full exception, something like that, right? You can do either of these two things. Then what I can do is that I know what is my front is, right? So if
Yes, sir.
it is indicated by f and if it is indicated by r, I should try to
Increment.
increase the pointer of f and try to store the value here, right? So what I can do is that I can do arr, and this f plus 1, or instead of this, I should rather like write plus f equals to data, right? Make sense? Tell me.
Yeah, fine.
But I see there is an issue here, some issue. What is that issue? Now, at least tell me now. Last time you guys didn't tell me. What is the issue now here?
Sir, when it reached to the last index,
Mm-hmm.
at that time it will increment first, right? In this case, index.
Yes. So if suppose I was here, right? If suppose if suppose the situation is like this, that this was also full 10 and it was 12, and suppose I had already dequeued once. So if I dequeue it once, so this place was zero position was filled. So the next thing that I have to add was that I had to add into this position. But what I did 6 plus plus. I did a I did a 6 plus plus. So now what it happened? It happened 0, right? It happened 0. So 6 plus 1, if I do, it will become 7. So what I need to do here is that I have to again here ampersand it with the capacity. Does that make sense? Because if I do 6 plus 1, then ampersand by 7, then it will become 0 again. Making sense?
Yes, sir.
Hmm?
Yes, sir. Yes, sir. We
So
got clear.
it's clear, right? So if we write like this, array plus plus capacity, this is how we do a NQ, right? Uh, Now the next thing that is left is DQ, and this is where we have to pay a great importance, because this is where you have to set the pointers back to -1 also. So the first thing that we do is that we'll do is empty, and in that case we cannot do anything to we simply return maybe something, some random number, or if you want you can throw exception also that the queue is empty and you're still trying to dequeue the element from it. Okay, but if it is not empty, now here the logic applies. What should we do now? So let me draw a figure of the worst case. So suppose I have only one element here. Okay, something like this. I have a circular queue, and this one, this one, this one, this one, this one, this one, and I have the elements like this. Say it is index 0, 1, 2, 3, 4, 5, 6, and suppose the element that I'm looking for is here. One element is here. Okay. And at this position, my at right now the rear is also this and the front is also this. So now you tell me, we have to remove this, that is for sure. So can I say like this? If first of all I'll have to remove the data, right? So what I do is that int data equals to array rear plus, or simply keep it, let's keep it simple. We first figure it out what is the array data at the rear, and then I'll have to do one more thing. R equals to R plus plus. This is normally we do know. If suppose it was, if I have to take out the 5, so initially my rear is here. If I remove out the 5, I'll move in this direction. So one index becomes two index. So it has now R. So I have to increase the index by R, right? This is what we normally do, right? Uh, Now one thing to be taken care of here, is this always correct, or do I have to take care of here also? Is this correct?
So if your rear and front is at the last position of this array,
Rear and front at the last position of this array here. Yes. So
yeah,
suppose 7 was here instead of this. So in that case, the rear becomes RR becomes equal to 7. That will be a problem. So again, we'll have to very nice. So we'll have to do it with the capacity so that it
yeah.
stays in the range. Okay. Now, once I have done this, so my rear has also moved apart, and no more element is left now. But suppose this is the situation. In this case, my rear has now become equals to 7. Sorry, rear has now become equals to 0, right? But now if I do an empty check, I'll check on the rear or I'll check on the front, and those values are not -1 right now, right? So this will not, if I do empty method call as empty, it will not return me true. So what should I also check and do in this case, so that if there's no element, I set those pointers equals to -1 correctly? What should I do?
So
Tell me.
inside this function, before after checking is empty, I will check like if rear is equal to front. At that time, I will just return front is equal to -1 or something like that.
If rear is, yeah, a very good idea, I think. So what you can do is that you can just keep some boolean. boolean is last, something like this, and this value is equals to uh, this value can become equals to if front equals to rear. In that case, you set it as true, else you set it as false. Like this, you can write this statement. This statement is clear to you guys. I've written it like in a vertical direction. Boolean is last is equal to front, or if the front is equals to right, it means the boolean is last will be true, because that is the only if there's only one element, then only the both the rear as well as the front indexes will be same. Otherwise, it will be false. And if that is the case, after doing this, since it was the last element, I have already removed it. So if is last, what I can do is that I can set front equals to -1 and the rear is also equals to -1, and then I return data. So again, if that is the case, once I've removed this, everything will get reset. So every time, the next time when I add, I will again start adding elements from here. Make sense? Clear to everyone? Vivek, Jahir, Paritosh, are you guys clear?
Yes.
Perfect. Cool. Very nice. So with this, we have completed the implementation of uh, a queue with the help of an array. Okay. Now it looked like that it is a circular array, but we have used only the linear array. Okay. So the first challenge was that wastage of space that we have removed by implementing the array as a circular array, right? But the another challenge that the queue has, that the array is always of a fixed size. That problem is not solved yet. That problem is not solved yet. So how can we solve that problem, guys? We have two problems, right? One was the wastage of space. We had sorted it now. The another problem was that in the case of the array, there's a fixed size, right? So if we have to fix that issue, one of the approach can be just like how we did in the case of the stack. We keep a dynamic size array, right? We keep on doubling the size of the array once it reaches its full capacity. That is one approach. What was the another approach that we did in the case of the stack, if you remember? What is the another data structure that we used?
Linked list.
Just
Linked list, right? So if we use linked list, again in the linked list, since the size can be increased dynamically, right? The size can be increased dynamically. We can use linked list as a data structure again to implement the queue as well, right? So let's try to see that. Okay, so we are trying to now again I have a queue. So for the first time, the queue I have trying to add an element into the queue. What should the first thing that we should do here? What should we do? We can create a linked list, a node of size 5, and this is pointing to the null, right? And here head is equals to tail equals to 5, right? This is the first thing that we do. If I do q dot in q1, what should I do now? Should I make one as a new head, or should I make one as a new tail? What should you do? What will you do?
should we assign head to one, because
Now
anyway
it all depends on how you want to do. So normally in a linked list, from the head we move towards the tail, right? From the head we move toward the tail traversal. So you can decide on whether you want to keep front as your head, or if you want to keep the tail as your front, right? So for example, if you suppose you want to keep head as your front, in that case you should go add one in the head. But if you want to have a definition that no, I want to keep my tail as my front, so I can go add an one at the tail. So for example, we have decided that my front will be head, and suppose my rear will be tail. Okay. Suppose this is the case. So the front is the head. So in that case, I'll go and create one as the head and I'll add like this. But I'll keep a track of who's my head and what is my tail. So this is my front, which is a head, and this is my the rear. Again, when I go and add 7 into it, right, again the 7 will get added here, 7, then 1, then 5, and this will be my front, and this will be my rear, right, and this will be pointing to the. Now when I do a dq, so whenever when I do a dq, we always go and dq from the rear, since I already know what my since I already know what my rear is. Now there is a problem when I keep the front as the head and the rear as the tail. Can you guys tell me what is the problem? The problem, the real problem is, right? So suppose now I have to DQ thing, right? So when I have to DQ thing, I have to basically return 5, right? So basically, this element has to be reduced, and my new tail should be this. This should be my new tail. But to make this new tail, I cannot go back because it is a single linked list, right? In a single linked list, you can only move in one direction from the left to right. So in a constant time, you cannot go to the previous step. For that, to coming to the previous step, you have to start coming from this direction, right? So to start coming from this direction, keep on traversing, coming to the second last position, that will take linear time. That will not be a constant time, right? So whenever you are trying to DQ element, you have to again reset the rear pointer. But resetting the rear pointer to the previous element is not possible efficiently in the case of a single linked list. You will have to, traverse the whole thing again from the head to come to the second last position, and this will not be done in the constant time. So in this case, the DQ operation will start happening in a linear time and not the constant time. So
Yes, sir.
how to sort it out? Can you think of any solution how to sort it out? What we can do here is that we can just change this. So instead of keeping the front as a head, we keep the front as the tail and the rear as head. So with this, what happens? Let's try to see it. So initially, say 5 was added, so we created a node of 5, and this was pointing to null, and this was my head also, and this was my tail also. Basically, this was my front also, and this was my rear also. Okay. Then I go and add 1 to it. So the 5 remained the same, and then I added 1 to it. Okay, so this my became front, and this is my rear. Now again I added 7, 5, 1, and then 7. Now 7 is now my new front, and this is my new rear. Right. Now when I have to do a DQ, I can simply go ahead. So DQ will return me 5. So I'll just go and take it out from here, and I just move head is equal to head dot get next. So I'm just left with this one 7. So this is my front, and this is my new rear. The issue was happening only in the case of when I'm trying to DQ, when I'm trying to delete a node. So when I'm trying to delete a node, I can always move from the left to right. That was not a problem. The moving from right to left was a problem. So if we just change and we keep the rear as the head and the front as a tail, this problem gets sorted out. Cool. So this implementation I'm not going to write. So this will be an assignment for you. So implement queue using linked list. Okay. And even the previous implementation that I wrote, please try to write the implementation of that in your language of your choice. Okay, so please implement queue using array, as well as please implement queue using linked list. Please use these two data structures to implement queue. Now let's move to the next thing. So let's start talking about what are the different kind of problems that can happen in the queue. What are the different problem patterns with respect to the interviews? Because again, queue, stack, linked list are the kind of topics which I feel if you have done it clearly, there's a 100% guarantee that you'll be able to solve in the interview. So these topics should be done very thoroughly. So let's try to move on the different kind of question patterns that we have. So first kind of the question pattern is that around interconversion of the stack into the queue and the queue into the stack. So right now, so far we have seen that we have implemented uh, queue using the array. We have implemented queue using the linked list. Now, this is another question in which suppose you have been told that you are allowed to use stack. You are allowed to use a stack data structure. Now, you have to implement a queue using the stack operations. Okay. So basically, if you have to implement a you have to implement two operations. So you'll have to implement one is enqueue, public enqueue, and data. And another thing is that public DQ, public int DQ, and this is queue data structure. I have to basically implement both the methods of enqueue as well as the DQ using stack. Using stack. Can you guys think of how can we do it?
Can we use multiple stacks?
Yeah, you can use multiple stacks.
So I think that I will use two stacks, right? So when I'm
Okay,
just yes, sir, when I'm just in queuing first, I will push element in the first stack.
okay. So let me draw two stacks here so that we all are following together. So suppose you're saying that I will create two stacks. Okay. So suppose I have a stack one this and I have a stack two this. So this is my stack one and I have a stack two.
So sir, when I'm in queuing element, I will push the element to stack one.
Okay. So for example, say in the queue we are first saying I'm in queuing. So I'm in doing indicating in queuing by E. So I say in queue one. Suppose right. So if I did one, should I push it to one here?
Yes, sir.
So this can happen. So this can happen in the constant time. O of one time it will happen. Okay. Now, if I suppose again I say E2,
Sir, I will push into S1.
again you will push into this one.
Uh,
Okay. So again this will happen. So that is sorted. So in queue operation is happening in my constant time. You are blindly pushing the elements into the stack one and it is happening in O of one time. Very
yes,
nice.
but
Okay.
I don't
But
think so.
when I do a DQ, how it will happen? What will happen in the case of the DQ?
Sir, it will not happen in like order of one. So in my case, I thought that like I will whenever I had to DQ, I will pop up all the element into S2 and then I will pop element from S1.
So yeah, so basically when I have to implement queue using a stack, there will
Mm.
be few limitations. I may not be able
Okay,
to
sir.
do both the NQ as well as the DQ operation in a constant time. That is there. So if suppose you're not worrying about the time complexity thing, then what should have been your approach? You will try to pop all the elements from here to here. So basically you will pop two here first,
Mm.
and you'll keep on doing till you're left with the only one element in this, and
Okay.
whatever the last element is there, uh, that will be the your result, right? So this will
Yeah.
happen in O of n time.
End time.
O of n time. So basically, uh, when you are implementing a queue uh, using stack, you can optimize one of these two. Either you can optimize the NQ or you can optimize the DQ. So in this case, you have optimized the NQ. So you have made the NQ as a constant time operation,
Mm.
but the DQ is a linear time operation. But if I tell you, suppose I want to optimize on the DQ, and you can make and because DQ is something I'm doing more. So what you do in that case? Are you guys getting my question? In this case, there are two operations, NQ and the DQ. NQ is very much optimized because I'm blindly going and storing the element into the first stack, right?
Mm.
So that pushing into the stack is a constant time, so the NQ is happening in the constant time. So I just do that. In the case of the DQ, now there is a problem. So what happens whenever I have to DQ, I keep on popping the elements from the first stack till only one element is left, and then that final element is my answer, which I have to return as the DQ. Everybody is clear on this?
Yes.
Perfect. So in this scenario, the time complexity of the NQ is O of 1, which is a constant time complexity, and the time complexity of the DQ operation is linear, which is O of n. But suppose if I tell you, I reverse this, I want you to say that I want to more optimize DQ and I can, compromise on NQ. What should we do in that case? So basically, DQ has to be done in a constant sense. So basically, I have to just do a pop, and that should return me the smallest element. That should be my criteria. Okay. So I can take two stacks, stack S1, and I take stack S2. Okay. First of all, first element came, I just go into this one since there is only one element. Now when I have to push in another element two into it, okay, and I have to push another element two into it, what I do is that I start popping all the elements from the one, okay, and moving it into the S2 till the whole is empty. So it became one here. Okay. And after this is done, then I put two here. Okay. After this is done, I then put a two here. Now again, when I do, again if I have to include three, and once this is done, I again replace it. So now this is my S2 is full and the S1 is empty. So whatever stack is full right now, I'll try to include again in that. So again, this is having two and the one. It is having two and the one. So what I'll do is that I'll take out two, I'll take out one. Okay. The way I try to do is that I'll try to push into the bottom, right? So here I'll again it will push one at the bottom, right? And uh, first the two will be pushed, and then when I'm trying to push one here, I'll try to push one into the bottom, so one get pushed here. One come here, two comes here, and then finally whatever the three comes here. So this will take linear time to achieve this thing, as we did in the case of the stack. We saw it last. And but now whenever I have to do a DQ, I don't have to worry about always, what I need to do. Any stack which has the element, I have to just top, remove out the topmost element of it, and that will be my DQ. So DQ will happen in a constant time, but the NQ will become little complex and it will start taking the linear time to solve the problem. Clear?
Yes,
Any
sir.
doubt? I'll again repeat. Okay. So this problem is basically has two subtypes. One when it is more optimized on the NQ and less optimized or compromised on DQ. Another way it is more optimized on DQ and compromised on the NQ. Right. So you need to. We've already discussed the logic. So I expect you guys to implement this problem. Now this problem logic we have already done. So writing codes is one of the easiest thing to do. So I am expecting this. In the previous one, I was trying to implement queue by the stack. Here I want you guys to implement stack using queue. So you will have two methods, public and pop. Okay, the stack has two methods. And there's a method like public void push, and this is int data, right? So you have to implement two methods of the stack, push and the pop, using the standard queue methods. So there are four standard queue methods: is empty, is full, dq, and queue. You have to use only these four methods to implement the stack. Okay, and again it can be maybe it can be more optimized on one of these two and compromised on the other. So maybe like push is more optimized, pop may be compromised, or sometimes pop can be optimized and push can be compromised. So I want you guys to think in both the directions and implement it accordingly. So with this, I've pretty much covered what all that I planned for the today's session.